Vitamins and minerals, iron. We will now talk about this next nutrient involved in blood health. We can see here that the human body contains approximately 2 to 4 grams of iron, with women having approximately 38 milligrams per kilogram and males having 50 milligrams per kilogram. The majority of the body iron exists in hemoglobin, 10% is within myoglobin, 1.5% is involved as a cofactor for various enzymes, and 20% exists in the blood and in storage. With iron, there are two primary oxidation states that are functional in the body. These include both the ferrous and the ferric form. The ferrous form is the reduced oxidation state, and the ferric is the oxidized form. Various processes and different characteristics as it relates to iron will be linked to either ferrous or ferric iron, and we will emphasize this throughout the slide presentation. Here we see the food sources of iron, and this will be separated into sources of heme iron and non-heme iron. Heme iron is found in the tissue of animal products, so you see here meat, fish, and poultry will be primary sources. Non-heme iron comes from plant-based sources. We see here nuts, fruits, vegetables, grains, tofu, and dairy. We also get iron from fortified foods. We can see here that the typical U.S. diet contains approximately 5 to 7 milligrams of iron per 1,000 calories. We also discussed the role of vitamin C in enhancing iron absorption, and this is something you may have heard previously. We will talk about the mechanism where vitamin C enhances this process. We'll now talk about heme iron, and again we said that heme iron is this form coming from animal sources. And heme iron, as you can see here, is contained within what is called a porphyrin ring structure. And this is 50 to 60% of the iron found in the meat, fish, and poultry. So you see here, this is the porphyrin ring, and the ring complex with iron is called a metalloporphyrin. The iron within this porphyrin ring is the ferrous form, so this is ferrous iron within the porphyrin ring forming this metalloporphyrin. We'll talk about the unique process of the digestion and absorption of heme iron. So heme iron must be digested so that it is going to be cleaved from the globin portion of hemoglobin and myoglobin. So we consume heme in the animal products bound to the globin portion, so within that structure of either hemoglobin or myoglobin, so the globin portion will need to be cleaved. This is cleaved by different proteases within the stomach, but primarily within the small intestine. Heme iron, so within the porphyrin ring, is absorbed intact. So the ring with the iron inside the ring complex with the porphyrin ring is absorbed through this HCP1 carrier protein. So that stands for heme carrier protein 1. So the HCP1 transports the heme with the iron through the brush border membrane. Once the heme ring with the iron is within the enterocyte, the heme is hydrolyzed by the enzyme heme oxygenase, and this releases the ferrous iron from the ring structure, and then it is able to circulate freely within the intestinal cell. So next we're going to review a diagram of this process, and so this specifically that we will discuss is the digestion and absorption of heme iron. So that's this portion of the diagram. So we see that we consume animal products containing either myoglobin and hemoglobin. So it contains that heme bound to the globin portion. So we have these proteases as well as HCl, but primarily the proteases involved in cleaving the globin portion. And so here we have the metalloporphyrin ring with the iron complex within it, and so that ring structure will be absorbed by the carrier HCP1, and that brings the heme within the enterocyte, and then the heme oxygenase will act on that ring, which will free the ferrous iron that was previously complex within the ring structure. So from there we get the products, the protoporphyrin ring, which is the empty now ring structure, and then ferrous iron. We will now review the process of the digestion and absorption of non-heme iron. This will be iron coming from plant-based sources, not bound to the porphyrin ring. So it will just be free non-heme iron. So we can see here that the iron consumed from plant-based sources will be bound to other compounds, which must be hydrolyzed by gastric secretions in the process. The non-heme iron is going to be in the form primarily of the ferric iron, so the oxidized form, and it must be reduced to the ferrous form, the reduced form, prior to absorption. This process that reduces the ferric iron to the ferrous form begins in the stomach, so the acidity of the stomach, the acidic environment, will begin to reduce the ferric iron. However, some will remain in the ferric form as it is transported into the small intestine, so the remaining ferric iron will form ferric hydroxide or undergo reduction by what is called reductase, which is an enzyme embedded within the brush border of the enterocyte. We see here that a specific reductase, there are actually different reductase enzymes that are involved in reducing ferric iron, but a specific reductase called ferric cupric reductase is vitamin C dependent. So vitamin C will play a role in activating or allowing for the activity of this reductase, which converts iron from the ferric to the ferrous form. We see here that the main transporter for free ferrous iron is what is called the divalent mineral transporter 1 or DMT1. So this DMT1 transporter is used to transport the ferrous iron through the brush border membrane into the enterocyte. We will see that DMT1 is also involved in the absorption of other minerals. Interestingly, the synthesis of DMT1 is affected by iron status. We will see that with low iron status, so a lower intake or lower body stores of iron, will actually upregulate the synthesis of the DMT1. And this is to prioritize the absorption or increase the percent of iron that is absorbed. And we will actually see this with other nutrients as well. As intake levels decrease or as stores in the body decrease, the methods that will be allowing for absorption of those nutrients will actually upregulate. So as iron status lowers, the synthesis of DMT1 will increase. We will here see the process of the digestion and absorption of non-heme iron. So this is going to be this other pathway here where we get the bound non-heme iron from food sources. The bound non-heme iron will need to be hydrolyzed by proteases or other enzymes, and we see from there iron is freed in the form of the 3+ the oxidized ferric form. So we see that some of the iron in the stomach will be reduced due to the acidic nature. However, some of this will also be complex with different additional compounds or binders that would limit its absorption. So we see primarily phytic acid, oxalic acid, and alkaline pH, and other factors like divalent cations is going to actually increase the excretion of iron in the feces and limit its absorption. However, the iron that is reduced, so a good amount of it will actually interact with the DMT1 channel, and we see that the iron that is not reduced in the stomach, and so the iron that comes through the small intestine as ferric iron, will interact with different reductase enzymes that will allow for it to be reduced prior to interaction with DMT1 and absorption. And we mentioned previously that one of the reductase enzymes will be dependent on vitamin C, so that's going to be a mechanism that promotes the increased absorption of iron with the presence of vitamin C. So we can see that the goal here with the non-heme iron is to get to the ferrous form, and the ferrous form is able to then interact with the DMT1 channel and travel through the brush border membrane into the enterocyte. So now the process of the absorption of both heme and non-heme iron will result in the ferrous form of iron, so the reduced ferrous form of iron, circulating within the enterocyte. Just a few more comments on the factors influencing absorption. So when talking about iron, the percent of iron that is absorbed is relatively low. Non-heme iron, the percent absorption of non-heme iron is about 2 to 3%, meaning of all of the non-heme iron that we consume, only about 2 to 3% is actually absorbed. So that is going to be fairly low. There are different enhancing factors, and the main one that we emphasized was vitamin C. So with vitamin C or other enhancing factors, the absorption of non-heme iron, the percent that's absorbed can actually increase from about 2 to 3% to 8%. Heme iron percent absorption is going to be higher, so the average percent absorption of iron is going to be about 10 to 18%. If someone is deficient in terms of iron, they have low intake or low body stores, we talked about how that's going to upregulate the synthesis of the DMT1 channel, so it's going to increase those channels and the capacity for absorption. So in deficient individuals, then the percent that's absorbed can increase up to about 35%. There are additional factors here, so if someone has a malabsorption syndrome, so if their ability to absorb nutrients is going to be decreased due to maybe a factor affecting the enterocytes or the villi or the microvilli or other factors, then that would limit absorption. Also, the absence of digestive juices or excess alkalinization of the GI tract, so it being more basic versus acidic, so the environment being less acidic, is of course going to reduce the ferric iron being converted to the ferrous form, which also would limit the percent that could be absorbed. So now that we have the ferrous iron, either through the absorption of heme or non-heme iron, we have the ferrous iron that is circulating within the enterocyte. There are several fates of the ferrous iron. So that ferrous iron can go through one of three main pathways. So first we can see that it can either, the ferrous iron can bind to cytosolic proteins, so proteins within the cytosol of the enterocyte, and used within the cell. So the first fate of the ferrous iron is that it can be used within the cell for a given function or purpose. The second fate of ferrous iron is that it can be stored in the form of ferritin, and this storage fate increases as the percent and the amount that is absorbed increases. So as more comes into the enterocyte, more will be stored. Just a note on the storage of iron as ferritin, the iron stored in ferritin is in the ferric form, so the 3+ form. So to go from circulation within the enterocyte to be stored as ferritin, iron needs to be oxidized. Lastly, the fate is that the ferrous iron can be transported out of the enterocyte via this protein called ferroportin. And so during this process of being transported out of the enterocyte, the iron becomes oxidized to the ferric form by this compound called hephaestin. The reason that it is oxidized by hephaestin is because once in circulation, iron will attach to this protein called transferrin, and transferrin will transport the iron through circulation and for uptake by different tissues. So we need this ferric form, this oxidized form, to be bound to transferrin. We can see here in more detail this function of hephaestin in oxidizing the ferrous to the ferric form as iron exits the enterocyte through the basolateral membrane. We see that hephaestin is copper-dependent enzyme, and so as iron becomes oxidized, we see that the copper mineral here will become reduced. We see here the diagram of the enterocyte that we viewed previously. This also outlines the three fates of the ferrous iron circulating within the enterocyte. So first we see that it can be bound to cytosolic proteins and have a functional use in the cell, or it can be stored as ferritin. To do that, it will need to be oxidized from the ferrous to the ferric form, and when in the ferric form, it can be stored as ferritin. Lastly, it can be transported out of the enterocyte by this protein called ferroportin. It interacts with hephaestin in the process, becoming oxidized, so it can be picked up by transferrin for transport through circulation.